Binomials is our next topic, basically. So let's have a look at binomial expansions. Binomial, where does the name come from? Bi meaning two, nomial meaning terms, maybe. There's the very simplest binomial expansion I guess we could have. 1 plus x to the power of 0 is, of course, 1. 1 plus x to the power of 1 becomes 1 plus 1x. Now, I'm deliberately writing the coefficient of 1 in to illustrate our pattern. 1 plus x squared, we have learnt, becomes 1 plus 2x plus 1x squared. We've seen the cubic. And, of course, if you forget how to do it, we could just expand our last one by 1 plus x. And we get 1 plus 3x plus 3x squared plus x cubed. In fact, if you want 1 plus x to the power of 4, you could multiply that by 1 plus x, and you end up with 1 plus 4x plus 6x squared plus 4x cubed plus x to the power of 4. You end up with a pattern. Blaise Pascal, a Frenchman, came up with a pattern which is now known as Pascal's triangle. Yes, that first coefficient was 1, then the next one is 1, 1, and then 1, 2, 1. But right in such a fashion, the pattern becomes obvious. We add the 2 above to get the 1 below. 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. And you could keep going. 1, 6, 15, 20, 15, 6, 1. It's not a bad row, not my favourite though. 1, 7, 21, 35, 35, 21, 7 and 1. And it just, keeps going. Still not at my favourite. I mean, everyone has their own favourite row. I know you probably have your favourite row for Pascal's triangle. But there's one. This is a good one, but not the best one. Here it comes. Oh, yeah. This is the best one. Watch that. Wait, look at this. Look. That is beautiful. Look at that. 122, 10. 122, 10. In the middle, palindromic, 252. Ah, come on. That has got to be the best row of them all, doesn't it? That's my personal favourite row. You could keep going. There's 11. How far did I go? Oh, no, another one. There's 12. So, of course, now, if you have to expand out 1 plus 2x on 3 to the power of 7, we can now do it very easily. Like so. Very easily. Right? We just look along the row of Pascal's triangle for the coefficients. What's known as the binomial coefficient. So 1, 7, 21, 35, 35, 21, so on. And then the powers of 1 start at 7 and go down by 1. The powers of 2x plus 3 then go up by 1. The two powers should always add to be the power of the binomial itself, which in this case is 7. And then we just got a little bit of working out to do, and we have our answer in all its glory. But where is it really useful? You see, just imagine you're out shopping, and as often happens, a person comes up to you and says, "Excuse me, could you tell me what 0.998 to the power of 10 is?" To 8 decimal places. And of course you didn't have your calculator on you, so you don't want to be embarrassed. Yeah, that's all right, that's fine. And you think to yourself, well, 0.998, hang on a sec. I know the expansion, because 10's the best row, so we know this expansion. I know the expansion of 1 minus x to the power of 10. I also know that 0.998 is 1 minus 0.002. So I substitute into this expansion, but because they only wanted to 8 decimal places, I can stop once I get to cubed. Because to the power of 4 would go 0.0000000, like there'd be more than 8 zeros, so it's going to be 0. Every term after this is basically going to be 0, so I only have to work that out. And that, of course, is a very simple calculation. Because 0.002 squared is, of course, 0.00, keep going, 0, 0. How many zeros? 0. Come on, how many numbers after the decimal place should there be?
0, 0, 0, 0,
6. Good. You got 3 numbers after the decimal place, so if you're squaring it, you should end up with 6 numbers after the decimal place. So in the next one, it would be I'm going to have to count them here, so don't say too many. 0, 0, 0, 0, 0, 0, 0, 0, 8. I think I got it right. Which of course rounds up to be 0.00000001. So we've got to include that one, but the rest of them are all 0. And we get our answer. Is that just not a beautiful thing? And the person in the shopping centre says, thank you very much. And off they go. We have this expansion here, but we're not actually interested in the whole expansion. We're only interested in the term with x squared. We have to find that coefficient. I could expand the right-hand side out there, the 4 plus 5x to the power of 4, and I get all these terms. But as I say, I'm only interested in the one that produces x squared. So the 2 times the one that has 5x squared, and the 3x, or the negative 3x I should say. So the negative 3x would go with the term that has 5x. They will produce x squared. So in reality, I didn't really need to expand the whole thing out. I could have just said, oh, what's the binomial coefficient of this term? And just found those two. We end up with, there they are. So really I only want those ones. They only want the coefficient, so the x I'm not interested in either. So the 2 would have been times the 6, the 4 squared and the 5 squared. And the negative 3 would have been times the 4 cubed and the 5, giving us a total of 960. Well, I can see you're excited. So you can do 15, eh? There we go. Oh, by the way, I've asterisked number 1 because we've already done it.